Hello students, welcome to this analysis of GATE 2024 mechanical paper. This is Sekhar from M Sigma Gokulam. Hello my dear GATE aspirants, you must have given the GATE mechanical exam few hours ago conducted by ISC Bangalore. Okay, in fact with all my experience of GATE coaching, this is Sekhar from M Sigma Gokulam, with all my experience of GATE coaching for more than 20 years across India at various corporate GATE coaching centers. With all my experience, I can say that this paper is moderately tough, not very tough, not very easy. In fact, I can say this is easy to moderate. I will rate it as the between easy paper to moderate paper. As compared to the particularly GATE 21, 22, 23 particularly, in fact this paper is easier as compared to the last 2 years papers. If you just look into the previous papers also, you will come to see that. Actually, before exam, GATE exam, I was expecting that the paper would be a bit tougher because it is being set by the ISC Bangalore. Last time it has conducted in GATE 16. After GATE 16, ISC is conducted this year only. So that time it was a bit tougher. Actually, I expected that this year also it would be a bit tougher, but as against the expectations, the paper came to be moderately easy only. Actually, it is not tough paper, definitely I can say that. As compared to the last year and prior to last year, this paper is easier, and therefore the topper scores definitely will be increasing, and cutoff also slightly may increase as compared to the last year. Almost all the subjects, like whether you take the manufacturing or whether you take the thermodynamics or whether you take the fluid mechanics or even the strength of materials, the questions have come to be a bit easier as compared to the previous years. That is what my observation as compared, because I keep watching these papers for the last 20-25 years during the second week of February, the moment the exam is over. Of course, those days it was offline. After 2013 became online. So I keep watching. There were so many sets to do between 2014 to 19. Now it is only a single set. So with all my observation, I can say that this paper is easier to moderate. Now let me analyze this paper and these questions by considering each subject one after another. Come on, let us let us go into the paper. First, let me take the thermodynamics subject. In fact, 12 days ago, exactly 12 days ago, I had uploaded one video. What are the tips that should be followed by the students in these last 12 days? Just 12 days ago, I have uploaded. See, in that particular video, I had given many things. I have spoken about many things. What you have to refer, what you have to revise. Most of them has matched with this examination. You can refer to that video which I had given 12 days ago. That time when I was giving that video, I said that whenever, particularly in thermodynamics, whenever you are calculating the maximum work output or minimum work input required for driving the refrigerator or the heat pump, or maximum work output from the heat engine, think that that cycle must be a reversible cycle or a Carnot cycle, or a reversible heat engine cycle in case of the work producing cycle. If it is a work receiving cycle, it should be the reversed Carnot cycle. Look at this first question. 24,000 kilojoule per minute is supplied from 1200 Kelvin furnace. Find the maximum work. Look at this word. In that video also which I had given 12 days ago, I mentioned that whenever you are using that maximum or minimum, that particular words you are using when you are reading in the problem, strike that, imagine that it is a Carnot engine cycle or the most efficient heat engine cycle. So this is the Carnot cycle operating between two temperatures. Source temperature may be a furnace. From the furnace, heat is being derived, heat supplied, and heat is being rejected to the sink. Heat is being rejected to the sink at 300 Kelvin. Because of this maximum work, I can say it should be a Carnot heat engine, that much, or reversible heat engine. So then only we can extract the maximum work, because then only the thermal efficiency will be the highest. Maximum work will be the thermal efficiency of the Carnot, into heat supplied. Thermal efficiency of the Carnot is only a function of the temperatures between which the heat engine is operating. The thermal efficiency, what is the specialty of the Carnot heat engine? The thermal efficiency is dependent only on the temperatures between which the heat engine is operating. So many kilomole per minute. But answer may be asked in kilowatts. We don't know actually. Answer may be asked because these questions were received from the various students based on their memory based. See, one student may be remembering one thing and that may be contradicted by other student, but so all these questions were received based on the memory based feedback from the various students who have written the GATE examination. Therefore, the answers may be little bit this side or that side based on the data provided by them, but don't worry. So, but answer is asked in kilowatts, therefore you just divide with 60 to get the answer in kilowatts. That is very important precaution. I said in that 12 days back video I released. Answer, be careful about while typing the answer. In fact, in this particular GATE examination, there are about 25 questions, 24 to 25 questions, multiple choice questions were asked, and most of them are 1 mark. All the multiple choice questions, most of the multiple choice questions, where we have to pick up the one answer, will be only 1 mark answer. The 1 mark questions they have given. And all the any type, numerical type, we have to type the answer, they are all given for the 2 marks, and very few multiple selective questions, MSQ questions, 2 or 3 questions only, each of 2 marks they have provided. But most of the questions which were given for the multiple choice questions, it is only 1 mark, and NET type will be of 2 marks, almost all the questions of NET. Okay, this is the answer happened to be 300 kilowatts. This is the first question in thermodynamics. Look at this, and in that video which I had given 12 days back, I had clearly mentioned that most probably they may ask the heat engine driving a refrigerator or heat engine driving a heat pump. Same question was asked. Heat engine is driving the heat pump here. The work output of a heat engine operating between the temperatures 1000 Kelvin and 300 Kelvin is the work output of which is input to a heat pump operating between the temperatures of a. Actually, that was not typed properly. This question was given like this. This is 150. This is 150 kilojoules. Okay. And the heat rejected by the heat engine is given to a reservoir at 300 Kelvin. And it is driving the heat pump, right? And that heat pump is also extracting heat from a low temperature reservoir and giving that heat rejection to a 300 Kelvin. Maybe it is a room. 300 Kelvin means 27 degrees Celsius, maybe not a regular room. So this heat pump is extracting heat from a low temperature reservoir maintained at 280 Kelvin and giving that heat to a room. And this source, this heat engine source is supplying heat at the rate of 150 kilojoules. The work output of the heat engine is supplied to the heat pump. In fact, the net heat rejected to the reservoir at the temperatures 300 Kelvin is asked. That means the sum of Q2 and Q3 is asked. Okay, the sum of Q2 and Q3 is asked. And the problem can be solved only if you assume that both the heat engine and the heat pump are reversible. Then only the problem could be solved. Supposing if heat engine is reversible, okay, or running on Carnot, therefore the work output will be heat supplied into thermal efficiency. What is the thermal efficiency? 1 minus 300 by 1000. This is the work output. Okay, so you will get certain work output, that is what is the heat supplied? 150 into 1 minus 3 by 10, so many kilojoules. Then heat rejected by heat engine, that is Q2. Q rejected by heat engine, that is Q2 is equal to 150 minus work output according to the first law, work output of the heat engine, right? This is the heat rejected by the heat engine. And assuming that this heat pump is also operating on the reversible cycle, COP of the heat pump, assuming it as a operating on the reversible cycle, what is the COP of the heat pump cycle? TH minus TL divided by TH. What is the TH there? High temperature for the heat pump is 300. Low temperature for the heat pump is 280 divided by 300. This is the COP of the heat pump. Actually, he did not mention. He did not mention about the what kind of heat pump, whether it is a reversible or irreversible. But unless and otherwise you assume it as a reversible, we cannot solve the problem. Therefore, I have assumed it as a reversible heat pump, and this is also a reversible heat engine. And the COP of the heat pump is defined as, what is the useful effect for the heat pump? This is the useful effect. This is the useful effect for the heat pump. So, Q3 divided by work input. That work input of the heat pump is nothing but the Q3 divided by W output of the heat engine, because all the work output of the heat engine is used to drive the heat pump. Work output of heat engine. All the work output of the heat engine is used to drive the heat pump. So from this, because we know this COP, we know the work output of the heat engine from this equation. From this equation, we got the work output of the heat engine. Okay. And from this we can calculate Q3. Okay, we can calculate Q3 as work output of heat engine into ideal COP. That as also can be called as ideal COP or Carnot COP of the heat pump. You can call this as the ideal COP. So from that you will be getting the Q3. So what he has asked is, what is the total heat rejected to the room? There are two heat rejections to the room, one from the heat engine, another from the heat engine. Therefore, Q rejected or supplied to room, I can say. I would say rather it is a Q supplied to room is equal to Q2 plus Q3. Okay, this answer is 1620 kilojoules. Unless and otherwise if you assume both the machines as reversible, you would not be able to solve this question there. Okay. This is an excellent question. Yeah, this is a more important and more excellent question. This is more important. Look at this. This is a third question in thermodynamics. In thermodynamics, totally 3 questions being asked. That is 5 marks. Thermodynamics, it is this weightage. This year weightage is 5 marks. 2 marks question. I think 1 mark question. This is a slightly tougher problem as compared to the previous 2 problems. Initial pressure 140 kilopascal temperature and 350 degrees Celsius. 1 meter below there is a stopper. The gas is cooled to 25 degrees Celsius. Actually what gas he has not mentioned, but I would take it as the ideal gas, air. Ideal gas, because it is a data memory based question, no, it should be taken as air only, because people may not be sending it as a air. Ideal gas, okay. Then what will be the specific work done? Initial pressure is 140 kilopascal and initial temperature is 350. Okay. Then the gas is being cooled. This is a cooling, Q rejection to atmosphere. As the heat is being rejected from the gas to the surroundings, okay, the process contains, the entire process contains totally 2 different thermodynamic processes. Total events, there are 2 number of total events. As the gas is being cooled, the piston slowly keeps sliding down at constant pressure of 140 kilopascal. As you begin the cooling, naturally the pressure tend to decrease because of cooling. But to maintain the constant pressure, because there is already a piston weight is acting, maintaining that 140 kilopascal pressure. Slowly the piston is descending. And how long it will descend, how long it will go down till it falls on the stopper. There are stoppers here. Okay. Once the piston falls on the stopper, the further cooling cannot do any work there. So then the process would become constant volume. Initially there is a pressure. What is up? First let me give the data. P1 is 140 kilopascal. That is absolute only. Nothing about the gauge, because all the pressures used in thermodynamics are absolute pressures. No mention of the gauge. So initially the pressure is 140 kilopascal. As the gas keeps, you are cooling the gas, pressure must be tending to decrease. But to keep the pressure constant, the weight of the piston, which is until then being balanced by 140 kilopascal, slowly descending. Once that piston falls on the stoppers, there are stoppers here, right? Once it falls on the stopper, the cooling is continuing. Once the piston falls on the stopper, the further cooling will only reduce the pressure, but no further work done. Okay, so work is being done only during that constant pressure process, and beginning from that initial state 1 until the piston falls on the stopper. So we have to think that there is a work done. In fact, there is a work done on the system here because piston is descending. There is a work done on the system. There is a work interaction between the system and surroundings only during that constant pressure process until the piston from the starting position until it reaches and comes onto the stoppers. Once it falls on the stoppers, any further cooling will only reduce the pressure, will only reduce the temperature, but there will not be any change in volume and there will not be any change in work because it is a closed system. I already said in my online classes, online thermodynamics classes, I very clearly said that there must be 3 inquiries should be done. Look at the video I had given 12 days ago. Whenever you are analyzing thermodynamic process, you must be 3 inquiries. What is the nature of the system? Closed system. What is the nature of the working gas? Ideal gas, that is air. What is the nature of the process? First isobaric and then isochoric. Until it falls on the stopper, it is isobaric. Be any further cooling, it is isochoric, constant volume. So on the thermodynamic plane, it looks like this. On the thermodynamic plane, it is a 1 first process. 2 is the state when the piston just falls on the stopper. 2 to 3. This is the final. T3 is given. T3 is given as 25. Final. It is called final temperature after constant volume cooling. Of course, it could be put up on the temperature entropy diagram also. It is a constant pressure followed by constant volume. Constant pressure process is less steeper than the constant volume. This is 1, this is 2, this is 1, this is 2, this is 3. Okay, isobaric first and then isochoric. Work is done only during this. Work is done only during the 1 to 2 process. We have to calculate that work. Specific is the word he has used. Specific means what? Mass should be taken as 1 kg. Okay. Now you are interested in to calculate the work done during the constant pressure process. What is the formula? Pressure into change in volume, right? During the constant, assuming that the process is reversible, integral PdV we could write. Assuming the process as reversible, integral PdV we could write P into change in volume because the pressure is being constant. That is work of 1 to 2 only. That is P into V2 minus V1. Okay, because pressure is constant, we can write P1 V1 or P2 V2 minus P2 V2 minus P1 V1. We could write because pressure is constant. We could write it as MR T2 minus T1 we could write. Mass is 1 kg because he was asked for the specific work. Because we have assumed the working fluid as air or ideal gas. What is the R value? R value we know. R value is 0.287. R is 0.287 kilojoule per kg Kelvin. Gas constant of the air also know. So your objective is what will be the T2 just at that moment when the piston just resting on the stoppers. T1 is already given. What is the T1 given? 350 degrees Celsius. No temperature in Celsius. We have to add the Kelvin T2. So how to get the T2? 1 to 2 process is what? 1 to 2 is isobaric and the working fluid is ideal gas. We can write the Charles law that T2 by T1 is equal to V2 by V1. V2 is not given, but he has given the distances. We know the area. This is the area of the piston, right? So area of the piston remains constant. Area into what is this initial volume? This total volume will be 2 plus 1 because this area into this height will give the volume, right? What is that height? Area into 3 divided by No, sorry. V2 is here, right? When the piston is coming to here, that is a 2. That is area into 2 meters divided by what is the initial volume? Area into 2 plus 1, 3. Area into 3. Area will get cancelled. You will get the T2 in Kelvin only, that is 350 plus 273 into T1, that is into 2 by 3. T2 is equal to so many Kelvin. All temperatures must be in Kelvin, that is 415.33. 415.3 Kelvin. T2 we got it. Now once you know R, we know M is 1, we know T2, we know T1. Specific work. Specific work means work done per kg. The meaning of specific work is work done per kg is equal to 1 into 0.287 into T2 is 415.3 minus 350 plus 273. That is the T1, right? So this will give the work done. You will obviously get a minus work done on the system, that happened to be minus 59.60 kilojoules. Take care of the units. Kilojoules per kg, automatically it is kg. Specific means work mass should be taken as 1. It's a very good question. First the process is isobaric, then followed by isochoric. Isobaric followed by isochoric. Same question was asked again, conducted by the IIC 6 years ago in 2016 paper. Just look at that 2016 paper. Same question, if you just recall that question, but it is exactly reverse. There were stoppers. On that there is a piston is resting. This is gate 16. Conducted again by the IIC Bangalore. See the similarity, but there it was pure substance. It is not ideal gas. Analysis of the pure substance like steam is bit difficult as compared to the ideal gas, because dealing with ideal gas is quite easier, because we have got a plenty of relations. PV is equal to MRT, PV is equal to NRT, delta U is equal to MCV delta T, delta H is equal to MCP delta T, PV to the power of N is equal to constant. So many thermodynamic relations are handy when you are dealing with the ideal gas like air. But when you are dealing with the pure substance, one must be extra careful. The same question was asked in gate 16, but that is not cooling, rather it was heat supply. Same thing, similar thing, but here also initially the pressure was 100 kilopascal, 200 kilopascal is required to lift the piston, and our heat is keep on supplying, and until the piston reaches 50%, now the piston is here, piston is moving now, 50% volume has been increased. What is the change in entropy, and what is the work done, and in fact what is the change in entropy of the universe. So many things he has asked actually. What will be the final state, what will be the final dryness fraction, etc. is asked. But this is also stopper, they are also stopper. Now there it was heating, now it is cooling. There it was first constant volume followed by constant pressure, now it is constant pressure first and then followed by constant volume. Just exactly reversed. He has entire whole thing, he has made it reversed. But that problem was definitely a bit difficult as compared to this year paper, because ideal gas is quite easier to solve. That was the steam problem, a bit difficult, and we have to calculate the equate the specific volumes and calculate the dryness fraction and work done. There are 3 questions there, all are linked there. That was a linked answer questions, 3 questions based on one data. You can refer to that gate 16, again conducted by IIC Bangalore. That was a tough question. In fact 16 paper was tougher than 24 paper. That was the IIC Bangalore, this year IIC Bangalore. Actually no problem, but that question, that 16 paper was definitely a tougher paper as compared to this year paper there. So we got the answer. We got the answer as minus sign only shows that only work done on the system. Minus sign negative doesn't matter. Negative sign only shows that on the system, because work is performed, volume is decreasing, right? Work done on the system, that doesn't matter. You don't have to type the minus there, because he has just asked the magnitude there. We need to type only the 59.6. Don't type the negative answer like that. Right. Now the 3 questions are asked in the thermodynamics. Now coming to the power plant. This is the power plant. Power plant means, what is the first power plant that comes in mind? Steam power plant, which runs on the Rankine cycle. There are only 3 power plants we have: steam power plant, or a gas turbine power plant, or a hydroelectric power plant. That was not asked. Hydroelectric power plant comes under the a different domain where the water is the working fluid, where Francis Caplan and etc. the Peltier wheel. That was not, no question came from that. But from the 2 power plants, one question is asked from the gas turbine power plant, one question from the steam power plant. And when he is setting the question on power plant, first preference will be given to the Rankine cycle, because that is the standard thermodynamic cycle on which any steam power plant or thermal power plant runs. This question is asked there regarding the Rankine cycle. Which one of the following is not correct regarding the Rankine cycle? Superheating in a boiler increases the efficiency. Correct. Superheating in the boiler increases the efficiency. If we just look at this as the Rankine cycle, if you just look at this as the Rankine cycle, if you increase the superheat, supposing initially this is the expansion, if you increase the superheating, this superheating temperature, what would result in the thermal efficiency? Definitely it will increase the thermal efficiency. This question was asked many times in GATE. This is the boiler pressure, this is the condenser pressure, a typical ideal Rankine cycle. This is the superheat temperature. As you keep increasing the superheat temperature more and more and more, definitely your thermal efficiency will be greater. What is the reason? Means there is an increment of mean temperature of heat addition. In any Rankine cycle, you follow any method that would result in the increase of mean temperature of heat addition will finally result in the increase of its thermal efficiency. By providing more superheating of the steam, you can definitely increase the mean temperature of heat addition. That is the important clue. Mean temperature of heat addition increases because of this increase of superheating. Definitely that would result in the increase of efficiency. Correct. But you may ask, how long you can increase? Can we increase to 2000 degrees, 3000? No. Currently the maximum temperature employed currently will be around 700 degrees Celsius. That is also higher side actually. That is the highest side I am putting. Usually it will be around 550, 600 itself is very high. That because beyond that blades would not be able to sustain. The turbines blades, steam turbine blades cannot tolerate beyond the temperatures there. Currently highest T maximum, the current metallurgical limit that can be sustained by any steam turbine blades will be around 650, around 700 degrees Celsius, not above that usually. But if you provide more and more temperatures, definitely your efficiency will be more and you got an additional benefit. You got an additional advantage. Your dryness fraction also will increase. X increase, thereby your quality of the steam is increasing, thereby there will be a lesser turbine blade erosion. Turbine blade erosion chances will decrease. So that is the additional benefit you get. Blades are safe. They don't be subjected to any blade erosion. First is question is answered. Decrease in boiler pressure increase the efficiency of the wrong. That is wrong statement. In fact, if you provide more boiler pressure, your efficiency will be definitely higher. Nowadays we are using supercritical boilers, generating steam at a pressure more than 221 bar, which is a critical pressure of the steam. Most of the modern day steam power plants generating huge power, they are all employing supercritical boilers like Benson boiler, generating steam at a pressure more than the critical pressure of the steam. This is the critical pressure of the steam, 221 bar. Above that they are generating the steam. So, but if you decrease the boiler pressure, efficiency will decrease. That is, B statement is decrease in the boiler pressure increases the efficiency. Wrong statement, which is not correct. Decrease in the condenser pressure increases the efficiency of the Rankine. Definitely it is correct. C is correct, because as you decrease the condenser pressure, as you keep decreasing, the condenser pressure like this, supposing if you are going, but if you provide even a lower condenser pressure like this, if you just provide the lower condenser pressure, this is a CP1, this is a CP2, definitely your efficiency will increase. As you go down, as I can generally say, as the gap between the boiler pressure and condenser pressure keeps becoming more and more and more, your efficiency will automatically will increase. As you gap between the boiler and condenser pressure, as it keeps increasing, efficiency will be higher and higher. But there is one fiasco, there is one condition. As you are decreasing the condenser pressure, the dryness fraction of the steam is going to the dangerously low levels, which may cause the turbine blade erosion. And one more thing, we can't decrease the condenser pressure like anything, because the condenser pressure, what is the condenser pressure we are providing, that mainly depends upon the cooling water temperature we are providing into the condenser. See, because into the condenser there is a coolant going, cooling water. From where it is coming? From the river it is coming, or from the cooling tower it is coming. That temperature of the cooling water entering into the condenser to condense the steam, that will decide what condenser pressure you are getting. Definitely, no doubt that lower the condenser pressure, more the work output, more the efficiency of the Rankine cycle, no doubt about it. But the lowest limit, possible limit of the condenser pressure is again decided by the river water temperature or the cooling water cooling tower. From the cooling tower we are getting the water, right? That temperature, or rather we can say wet bulb temperature of the atmospheric air. They are all linked. Wet bulb temperature of the atmospheric air, what is the temperature of the cooling water coming out from the condenser or going into the condenser, and the resulting condenser pressure, they are all very closely interlinked. So there is a practical limit of the lowest possible condenser pressure. Usually, most commonly it will be around 10 to 14 kilopascal. I can say most of the Rankine cycle problem, you will see the condenser pressure, of around 10 to 14 kilopascal absolute. You can see any Rankine cycle problem. Boiler pressure will be maybe 150 bar or 100 bar or 200, like that, 200 bar, even more above that. But for all the practical purposes, the condenser pressure selected for any steam power plant or the Rankine cycle will be around 10 to 14 kilopascal. Answer is D, C is wrong. Decrease in the, C is correct, sorry. C is correct, B is wrong. The pressure of turbine output is governed by the condensing temperature. Yes, the pressure of the C. The condensation temperature, as you keep lesser and lesser, the turbine outlet temperature also will be lesser and lesser. D is also correct. So only one is wrong there. What is the wrong statement? B is the wrong statement. As you decrease the condensing temperature, naturally the turbine exit temperature of the steam also will become lesser and lesser, right? But there is one limit, I said. There is a practical limit for the lowest condenser pressure you are able to get. No doubt, if you get lesser and lesser condenser pressure, your work output from the turbine will be more and more, because you are providing greater expansion of the steam isentrically across the turbine. You can expect the more work. So fourth question is very good question, expected question from the Rankine cycle. And before that, there is one question we would like to solve, which is not written in the PDF there. Now I am stating that. That question is regarding the regenerative Brayton cycle. That is the regenerative Brayton cycle. What is actually regeneration means? Regeneration means transfer of heat within the cycle from higher temperature to the lesser temperature. Why it is done? To improve the thermal efficiency. Transfer of heat within the cycle from higher temperature to lower temperature, it is called as the regeneration. It is done in the Rankine cycle, it is done in the Brayton cycle, it is also done in the Stirling cycle. But wherever it is done, the final objective is improvement of thermal efficiency. Regeneration is primarily done for increasing the thermal efficiency. It is done in the Rankine cycle also, which is called as a bleeding of steam. But here it is done like this. If you just look at this, how the regenerative Brayton cycle looks like: compressor, there is a heat exchanger, there is a combustion chamber, there is a gas turbine. The gases, after leaving from the gas turbine, there is a combustion chamber where you are adding the fuel and burning the fuel. The gases leaving the turbine, exhaust gases, high temperature exhaust gases leaving the turbine, they don't go directly into the atmosphere. Rather they will go to the heat exchanger and then transfer that heat to the compressed air and then to atmosphere. So this is the meaning of the regeneration. The compressed air is the compressed air. This is a compressed air, right? The compressed air is getting heated up. Getting heated up in this counterflow heat exchanger. You can think of as the counterflow heat exchanger, also known as the regenerator. This is, you can think of as a counterflow heat exchanger. These hot exhaust gases are heating the compressed air, and compressed air is getting heated up by receiving the heat from, there is a transfer of heat. Of course, they don't mix up. This is the heat transfer. And he has given the temperatures there. He has given the temperatures. This is 300 K and this is 550 K, and the exhaust gases are coming at 800 Kelvin. Here it is after heat supply, it is 1200 Kelvin in the combustion chamber, and the gases are coming out to the atmosphere at 600 Kelvin. Gases, hot gases. The hot gases entering the regenerator transfer the heat and come out with the 600 Kelvin. Then what is the thermal efficiency of this regenerative Brayton cycle? I would just like to put up, from the TS diagram, on temperature entropy diagram, the Brayton cycle, ideal Brayton cycle with regeneration. He didn't mention anything about the machine efficiencies. All the processes I couldn't take it as the, I'll just put it as 1. This is to after the compressor 2. This temperature is after, this is 800 Kelvin, this is 1200 Kelvin, this is the turbine, this is the compressor, and this compressed air is increasing its temperature in the regenerator to the state 3. I can say this is state 3. This is 1, this is 2, this is 3, this is 4. This is 5 and this is 6, and the hot exhaust gases are cooled to the hot exhaust gases are cooled to the what is the temperature? 600 Kelvin. Are cooled to the 600 K, from 800 to the 600 K. Okay, there is a transfer of heat here. I am marking that transfer of heat. This is the heat transfer in a regenerator, which is a counterflow heat exchanger. Okay, now this is this temperature T2 was given as this is 300, this is 550. Then how to get the T3? Because you can write the energy balance, heat lost by the gases is equal to heat gained by the compressed air, right? Heat lost by gases is equal to heat gained by hot gases. Heat gained by compressed air. We can take that Cp of the gases and Cp of the air almost same. Mass flow rate of the gases and mass flow rate of the air also same, because gas turbines use very high air fuel ratios, 100 air fuel ratios they use. Air fuel ratios used are very high. Unlike in IC engines, gas turbines use very high air fuel ratios, around 80:1, 90:1 like. So we can think that they are almost equal. Mass flow rate of the gases and mass flow rate of the air almost equal. Cp of the gas. You can think that therefore at this temperature fall, Thi minus The is Tce minus Tci. So from which whatever this temperature fall is the temperature rise here 200. Therefore then what is this temperature? It will become 750 Kelvin. From this energy balance I can think that. Taking that mass flow rate of the gases and Cp are these two are equal to these two, and from the energy balance I can say it is 750 Kelvin. Then what is the thermal efficiency of the regenerative Brayton? Regenerative Brayton will be, we can use anything, work of turbine minus work of compressor divided by heat supplied in
combustion chamber, or general formula of the second law 1 minus QR by QS also we could write. So taking the Cp as 1, Cp of the gases as 1 minus, what is the Q rejected there? Cp into this one, Q rejected from here. This is the actual Q rejection process sectionally. This is the Q rejection process sectionally between 600 to 1. 600 minus 300 divided by Cp, because assuming that Cp of the gases and Cp of the air is same, what is the heat supplied between 3 to, this is the external heat supplied. In the combustion chamber, external heat supplied Cp into T4 minus T3, that is 1200 minus 750. You will get the answer for the regenerative Brayton cycle. Cp will get cancelled, assuming that Cp of the gases and Cp of the air is same. Heat supplied in the combustion chamber is here. Heat supplied in combustion chamber is between 3 to the 4. Try to understand the processes there. 1 to 2 is compression, isoentropy compression. 2 to 3 is the heating process, heating of the compressed air in the heat exchanger, heat transfer happening, which is also called regenerator or heat exchanger. And 3 to 4 is the external heat supply, QS. QS we are supplying here by burning the fuel. So that is the external heat supply between 3 to the 4. So Cp into T4 minus T3, that is the heat rejected, heat supplied. Q rejected is by the gases between 600 to the 1. That is the heat rejection process by the gases. They are taking the gases here. So that at 6 state, the gases are going to the atmosphere. What is the atmospheric temperature? 300 Kelvin. So you will get the answer. So very good question. This is regarding the Brayton cycle, regenerative Brayton cycle. Only thing here we have to assume here is specific heat of the gases and specific heat of the air are same, number one. And mass flow rate of the gases and mass flow rate of the air also same, because air fuel ratios used are very, very, very high. Okay, a little fuel is added. Supposing 100 kg of air is going, I may be adding just only around 1 kg of fuel. So the mass flow rate of the gases is almost equal to the mass flow rate of the air, almost, not exactly same. So we can almost take it as same. Right. So this is how we calculate the thermal efficiency of the regenerative Brayton cycle. Regeneration, always wherever it is done, it improves the thermal efficiency. Yes, this is another very, very important question, compressible flow. Last year also he has asked, 23 also he has asked. But this question, there is a shock. This is a question regarding the normal shock. What is shock? I have discussed that in my video also, which was given 12 days ago. I had talked about the shock also, and I defined the Mach number also that time. I defined the Mach number. Just look at the video I had given about 12 days ago. What tips you have to prepare before taking the gate. A normal shock is an abrupt and sudden deceleration of the supersonic flow into the subsonic flow. A shock wave will happen whenever a supersonic flow abruptly, suddenly decelerates into the subsonic flow, during which a great irreversibility prevails, resulting in increase of pressure, increase of density, increase of static temperature, and increase of entropy greatly, because there is a lot of irreversibility. But for the shock wave to happen, the flow must be, before the shock wave it should be supersonic, and after this should be m is greater than 1. This should be m lesser than 1. That is the shock wave. Shock wave, I am writing here, shock wave is an abrupt deceleration. Is an abrupt, very sudden, abrupt deceleration of supersonic flow of fluid. M is greater than 1. What is that M there? Mach number into subsonic flow. M is less than 1. Here is M is greater than 1. So what will change during the shock wave? Therefore, across shock wave, first I will put that will happen only in the, suppose if you just take the the pressure, this is the pressure. This is the pressure curve. Pressure keeps on decreasing, but across the shock wave, the pressure abruptly increases. Here m is greater than 1, here is across, this is here m is less than 1. So pressure static, so therefore during shock wave, what will increase? M decrease, Mach number decreases, no doubt. Static pressure increase because of an abrupt deceleration, but deceleration with a great irreversibility. Entropy greatly increases, static pressure increases, static temperature also increases, but stagnation temperature remains constant. Total enthalpy or stagnation temperature, total enthalpy also H naught is also constant. Static pressure increases, M decreases, and entropy increases, temperature increases. So density, of course, density will increase. Density increases. Along with the density, specific gravity increases. When the density increases, specific gravity also should increase, because specific gravity is, how do you define the specific gravity? Density of the fluid divided by the density of the standard fluid, that is water. Okay. So as the density of the fluid increases fluid, specific gravity also increases. We can accordingly answer all this. So please note that across the shock wave, the Mach number falls. Entropy increases greatly, lot of irreversibilities, highly irreversibilities prevail. Of course, there are two kinds of the shock waves, normal shock and oblique shock there. Static pressure increase, density will increase, pressure will increase. This is a static temperature, but not the stagnation. This is the stagnation. This is a stagnation enthalpy. This is a stagnation temperature. This is a static temperature. This is a static pressure. Pressure will definitely increase. And how about the stagnation pressure? Decrease. Stagnation pressure decrease. P naught refer to the stagnation conditions. Stagnation pressure decrease, stagnation enthalpy constant, stagnation temperature constant, but the stagnation pressure decreases, static pressure will increase, entropy will increase, static temperature will increase. All these things effects you can see here. You can easily answer whatever the options you may be remaining, but they are the effects here. If the answer option B, if you look at that, PE is lesser than PF, because pressure is abruptly increasing. Yes, PE is lesser than PF there across the show. That is correct. Rho E is lesser than rho F. No, this is wrong. Density will increase. Density will increase across after the shock wave. During the shock, after the shock wave, density will increase. Mach number at the E is greater than Mach number at the F. Yes, supersonic flow. This is supersonic. M is greater than 1 means supersonic. M is less than 1 means subsonic. Shock means that. Shock wave means abrupt and sudden deceleration or decrease of velocity from supersonic flow to the subsonic flow. Yes, coming to this, so power plant has given 3 questions, and coming to the most important subject, heat transfer, where there are asked the highest number of questions in this. 9 marks, 6 questions. 6 questions, 9 marks. He has covered all the 4 topics: conduction, convection, radiation and heat exchangers. All 4 topics he has covered, and 9 marks. Generally in gate 22 also he has given 12 marks. Look at the gate 22 paper. That was the toughest heat transfer paper in the recent years. Gate 22 in both the sets. There were 2 sets in gate 2, not last year, last before year. See the previous papers. That was the toughest heat transfer paper in the recent years. Gate 22, where non-uniform heat generation and thermal conductivity is a function of temperature. So there are so many variables he has changed there. But this year heat transfer is moderate, not tough, not easy, moderately he has given that. This is a question from the radiation. There are 6 questions carrying 9 marks from the heat transfer. Now the subject is heat transfer. Consider a question on radiation. Consider a hemispherical furnace of diameter 6 meters with a flat base. The dome of the furnace has an emissivity. This is an emissivity of 0.7. This is emissivity of 0.7. But this is black. This is black. And the base and the dome are maintained at the uniform temperatures of this is 300, this is 300 Kelvin, and that is 1200 Kelvin. Under the steady state condition, what is the net radiation of heat transfer? This is the same question asked in gate 14. You can see there. Gate 14 set to this question and that question same. I have done so many number of times in my earlier online classes also. So many number of times this question, but there, so it's slight difference. There, this was black, this was grey. Now here, this is black, this is grey. This is grey. This is black given, this is grey. But in that gate 14 question, roof, this one, roof was grey, roof was black and floor, that base was grey. Exactly as interchanged that. This is, and take this surface as 1 and this surface as 2. I famously known as, in my notes I always call it as the case 2 formula. In my heat transfer notes you will see that in the online videos, I had given two cases. Case 1 is the infinitely large parallel planes. Case 2 is the infinitely long concentric cylindrical surfaces. That case 2 formula, what is the speciality? F12 is equal to 1 and F21 is equal to 1. As long as these conditions hold good, we can directly write Q122 net radiation heat transfer is given by sigma T1 power 4 minus T to the power of 4 into A1 divided by 1 by epsilon 1 plus 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1. But with one precaution. This formula can be valid as long as these two conditions are satisfied, with only one precaution, that name the inner surface as 1. You should name that inner surface as 1 and the outer surface as 2. 1 is surrounded by 2. With that intuition, with that understanding, inner surface as 1 and outer surface as 2, this formula has been put up, which is also always in my notes, heat transfer notes on online or offline, always I used to call it as the case 2 formula. Okay. Case 2 formula is always applicable whether T2 is more than T1 or T1 is more than T2. Whether this is more or this is more, don't bother. Never bother. Just blindly you can write. If you get a negative answer, which you get in this case, negative answer only means that net heat transfer is from 2 to 1. Because in this case, net heat transfer is from 2 to 1 only, not from 1 to 2, because T2 is greater than T1. So net radiation heat transfer is from 2 to 1. So this formula, this problem should be done based on that application of the case 2 formula, wherein one shape factor is 1 and the other shape factor is less than 1. Yeah, look at this. F12 is 1. Look at this figure. F12 is 1 and F21 is less than 1. F21 is less than 1. You can easily see that. Yes, you could blindly write that formula. This is a case 2 formula I call. Therefore, Q122 net will be 5.67 into 10 power minus 8 Stephen Boltzmann constant, 300 to the power of 4 minus 1200 to the power of 4 into A1. A1 will be pi r square. R will be 3 pi r square divided by 1 by epsilon 1. What is the epsilon 1? Black. Black is epsilon 1 is 1. A1 by A2 pi r square by 2 pi r square. Right? That is the hemisphere area into 1 by epsilon 2. 0.7 minus 1. So many watt. This is the answer. You will definitely get negative. Negative answer only means that, negative answer only says that net radiation heat transfer is from 2 to 1. Net radiation heat transfer is from 2 to 1. That is the only thing, perception we have to take. But don't never type the negative. Never type the negative. It is only for our understanding. Net radiation heat transfer is from 2 to 1. From the roof, from the hemispherical dome to the base. Roof to the base. Same question in that gate 14 problem also. T2 is greater than T1. You can refer to that question also. Same question. But only thing is, there it was black, this was grey, now he has interchanged. That's it, nothing else, no change is done.
You can refer to that gate 14 set 2 question also. Okay, you will get the answer there. But look at the answer. He has asked in kilowatts. That means this answer will be in watts. You have to divide with 1000. Final answer should be very careful. It is asked in kilowatts, but we got the answer in watts. Minus sign only shows that net heat transfer is from 2 to 1. Don't type the minus, because always the heat transfer rate is from the high temperature to the low temperature. Radiation also obeys the Clausius statement of the second law, that heat always flows from high temperature to the low temperature. Net radiation heat transfer is from high to low. So from surface 2 to the surface 1. But formula will not change. Whether T1 is more than T2 or T2 is more than T1, formula will never change. Minus answer will give that, say that heat transfer rate is from 2 to 1 because T2 is greater than T1. This formula is applicable as long as there are only 2 surfaces, if these conditions are satisfied, and name the inner surface. Precaution is that inner surface is 1 and outer surface is 2. With that notion, this formula is done. Right. This is the question. This was also a previous question. Look at that gate 2013. There are these, but they are slightly different. A rectangular slab without internal heat generation. No Q dot. No Q dot. Okay, Q dot is 0. No internal generation. And thermal conductivity, it is a variable thermal conductivity, A plus Bx. This is x direction, positive x direction. Positive real numbers. Okay. Which of the following variation of temperature, x is constant? He has given these variations like this. Temperature versus x. All the curves are temperature versus x. Yes, given that. Second thing, fourth one is irregularly given. That is. The problem can be solved based on the fundamental equation behind the conduction. What is the basic fundamental equation behind any conduction phenomenon, heat transfer phenomenon? Fourier law of conduction. The basic law is that Q, the rate of heat transfer by conduction, is minus Ka dt by dx. Okay, minus Ka dt by dx. Dt by dx is the temperature gradient. But in this case, in this problem, this is 0 degrees Celsius. This is T2. That means heat transfer is in the positive x direction or a negative x direction. Definitely he has given 0 means this T2 will be greater than 0. T2 is greater than T1, right? That means heat transfer always occurs from high temperature to the low temperature. This is the direction of the heat flow, right? So therefore I should write a plus. I should write a plus there, because as x is increasing, temperature is also increasing. Therefore plus heat transfer happens in the high temperature to the low temperature. Q by A. What is it? K A plus Bx into dt by dx. In this particular equation, he has given steady. It is a steady state. It is a steady state heat conduction. During the steady state heat conduction, if you take a differentially small element, this Qx and Qx plus dx should be equal. Qx and Qx plus dx should be equal. That is, Q is not a function of x. Why? What is the reason? Since steady state, you will take only steady state, if not mentioned, steady state and no heat generation. That is important. If heat generation is there, again it will becomes a function of x. Because no heat generation, Q is not a function of x. Steady state and no heat generation. But steady state, if there is any heat generation, Q will become a function of x. But here no heat generation, steady state, Q is not a function of x. Qx and Qx plus dx are same. A is a constant. A is not a function of x. Why? Slab geometry. In slab geometry, A won't change in the direction of the heat flow. That point I have many times I said in my heat transfer videos or notes. So A is not a function of x.
Q is not a function. Therefore, Q by A is not a function of x, is constant. When Q by A is constant, A plus Bx into dt by dx is constant. That is, as x increases, because A plus B are positive numbers, as x increases, k increases. K increases means dt by dx must decrease. Dt by dx must decrease. That you can see here. Dt by dx is a answer will be there. See, look at this. This is a dt by dx more. This is a dt by dx lesser. So as x increases, dt by dx, answer is A. Same question was asked in GATE 2013. If you just look at the GATE 2013, the last offline paper, the k was function is given as k0 plus bt, where k0 and b are positive constant, positive values. Same thing. This is also that and these are same. But there k was given as a function of t. Here the k was given as a function of x. Obviously, when k is a function of t, obviously k becomes a function of x because t is a function of x. If t is not a function of x, there is no heat transfer at all along the x direction. What is the reason behind the conduction heat transfer? Because temperature gradients are existing. Temperature is a function of x. Okay, if k is a function of t, automatically k becomes a function of x because temperature is a function of x, and heat transfer is happening along the negative x direction because this is given as 0. I suspect that this temperature may be more than 1. So this is the temperature profile. This is the temperature profile. Okay, this is the d square. I can say d square t by dx square is negative. I can say is negative. Slope is decreasing with x. Okay, so this is a very good question. Simple question only. It's same repetition of GATE 2000 question, but there it was a temperature function. Now it is a k is given as a function of x. You have to understand main contention here is q by a is not function of x because q is not a function of x, steady and no heat generation. Area will not change in any slab case of conduction. Area of heat transfer will not change. Area of heat transfer will change only in the radial conduction heat transfer through a hollow cylinder and radial conduction heat transfer through a hollow sphere. Only those two geometries, cylinder and sphere, area of heat transfer changes in the direction of heat flow. But in case of the slabs, area of conduction heat transfer remains constant in the direction of heat flow. If this is the direction of the heat flow, what is the area of conduction according to the Fourier law? The area perpendicular to the direction of heat flow. If this is the direction of heat flow, area perpendicular to that is that. That won't change in case of the slabs, right? So answer is A. This is the answer. This is a question with heat generation. I have told in that video also, tips of GATE 12 days ago. Heat generation should be definitely given. This is given again. A uniform heat generation, look at this. Uniform heat generation, he has mentioned there. This Q dot, this one is only called as Q dot, 100 into 10 power 6. This is 150, this is 110. Nothing was insulated. Where is the location you get the maximum temperature? That was question in the given in the earlier GATE also. There is a linked answer question. Where is the location of maximum temperature and how much is that maximum temperature is asked. Now that was a linked answer question given long back around 2006 or 7, those days actually, and that was a linked answer. And this is the this is only one question. Definitely this is more temperature, this is less temperature, uniform heat generation. What will be the temperature profile? Definitely I can say it is an unsymmetric parabola. Unsymmetric parabola with maximum temperature in that half, with maximum temperature in that half where the high temperature is there. This is 150, this is 150, this is only 110. So this distance we have to calculate. So I begin to measure the x from the left side, because the location of the maximum temperature from left face, x is equal to 0 here, okay, here x is equal to 0.02 meters, here x is 0 I have taken, because he asked that, and we can begin from the fundamentals. D square t by dx square plus q dot by k is equal to 0, integrating dt by dx minus q dot by k into x plus c1, again one more integration, minus q dot by k into x square by 2 plus c1x plus c2. C1 and the c2 are constants of integration. I integrated twice. Q dot is the heat generation. How to obtain those constants of integration? From the boundary conditions. Look at this boundary condition given at x is equal to 0, 150. At x is equal to 0, 150. If you substitute there, 150 is equal to C2. At x is equal to 0.02, the two constants of integration must be obtained from the two boundary conditions. What is the temperature there? T is 110. So 110 is equal to minus, what is that, q dot, 100 into 10 power 6. Take care of everything in watt per meter cube. K value is given. K value is given as 200. In that gate problem also which was given, that was also 200. I still remember, that was also 200. But there it is 80 megawatt per meter cube. 80 megawatt. Here it is given 100 into 10 power 6 watt per meter cube. Minus q dot by k into x value will be, what is x value? 0.02 plus q dot by k x square by 2, x square by 2 plus c1x, c1 into 0.02, substitute that c2 value, plus 150. From this you have to calculate the c1. Calculate the c1. Once you get the c1, the temperature is maximum, the temperature of slab is maximum at the location where, the dt by dx is 0, at the location where dt by dx is equal to 0. We know the dt by dx here. Put dt by dx is equal to 0 minus 100 into 10 power 6, k is 200, x value plus c1 you are obtaining, you just substitute that c1 here. You will get the x as 0.006 meters, that is 6 mm. 6 mm from the left face. This is the T max. This is the location of T max, 6. That gate question he has got as a 5 mm. In that gate question, still remember, that was 5 mm. Now it is answer is 6 mm. This q dot is also same, dimensions also same question. But only thing is, in that gate question he has asked what is that maximum temperature. How to get that, what is that maximum temperature? You put this value of x in this temperature distribution, here in this temperature, because this is the temperature distribution. We know that C1, we know the C2. What is C1 here? C1 is already, C1 is obtained from this, C2 is 150, C2 is 150, C1 is obtained from this equation, and then at any x we can calculate the temperature. If you put x is equal to 6 mm here, you will get that maximum temperature. It is an unsymmetric parabola, okay, unsymmetric parabola. With that, maximum temperature will be existing in the left half. Why in the left half? Because left hand side temperature is more than the right hand side temperature. That will be in the left half. Yes, this is the question given from the convection. Consider incompressible laminar flow over flat plate. He has printed as flat, flat means flat plate there. Consider incompressible with a free stream velocity of u infinity, symbol is u infinity. Okay, there is a formation of hydrodynamic boundary layer and
thermal boundary layers. On the flat plate, there is a heat transfer happening. If the free stream velocity, this is a free stream velocity, gets doubled, if the free stream velocity is doubled, what was the Nusselt number? How many times the Nusselt number changes? So it is a flow is laminar. What is a flow is laminar means? The local Reynolds number at the trailing edge should have been lesser than 5 into 10 power 5. Then only it can be termed as laminar flow. Otherwise, it can't be called as a laminar. Okay, for flow over flat plate. Okay, for a laminar flow over flat plate, this is the correlation for laminar flow over flat plate. What is the correlation for calculating the convection heat transfer coefficient H bar, average convection heat transfer coefficient 0.664 REL to the power of R, PR to the power of 1 by 3. But PR is fluid property, Prandtl number is fluid property. See, as long as the fluid is same, Prandtl number remains same, mu Cp by K is remains same because PR is the fluid property, same fluid, but only as changing the velocity. Where is that velocity? REL is there, V infinity, average local Reynolds number at the trailing edge. This is the average Nusselt number, this is the average convection heat transfer coefficient, V infinity into L by nu, kinematic viscosity. This is U infinity, actually symbol is changed as U infinity. Only this got doubled. When this gets doubled, how many times the Nusselt number will increase? Root 2 times. If U infinity gets doubled, Nu increase by root 2 times. Look at this, power half is, look at the power half there. Only in the Reynolds number that free stream velocity is there. Answer is A. Answer is A. Nu increase by root 2 times. Look at that, you substitute this one. Prandtl number won't change, same fluid, same Prandtl number. Kinematic viscosity property, constant. Yeah, this is a question on heat exchangers. He has covered all the 4 topics: conduction, convection, radiation, heat exchangers, everything. All type, 9 marks, 6 questions. All the 4 topics were covered in a shell and tube heat exchanger, single shell and 20,000 tubes. It is a big shell and tube condenser maybe. 20,000 tubes are present in one single shell. Imagine the size of the heat exchanger. Okay, the steam is condensing. Always steam on the shell side. Always steam on this. Remember, in any shell and tube heat exchanger, condenser particularly, always steam on the shell side, cooling water on the tube side. Why? What is the reason? To maintain the vacuum. You get a huge vacuum. To maintain that vacuum easily, steam is always provided on the shell side, and always inside the tubes it is always the cooling water. By default it is like that. Okay, fine. Steam is condensing at what temperature? 50 degrees. When the steam is condensing, its temperature will not change. Thi is The, and the water flow at the rate of enters the tube at 30. TCI is 30 degrees Celsius. TCE we don't know, is not given. This is a cooling water. This is a steam condensing. When steam condensing, it liberates latent heat. The temperature of the steam will not change. Whether you draw the parallel flow or counter flow does not matter. When one fluid is undergoing phase change, in any condenser, in any heat exchanger, it does not matter what type of heat exchanger you are going to design, because LMTD value, effectiveness value, area, everything remains same between parallel flow, counter flow and cross flow. So it does not matter. It does not matter what type of heat exchanger we are going to select if one fluid is undergoing the phase change. THI is equal to THE. THI is equal to THE. Hot fluid temperature won't change, but it is rejecting heat. Temperature is not changing. Temperature is not changing, but it is rejecting heat. What heat it is rejecting? Latent heat, which is given. Latent heat is given there somewhere, 2.2326 megajoule per kg. What is the effectiveness of the heat exchanger? Actually, this problem
to calculate effectiveness of the heat exchanger, one special formula is there, 1 minus e to the power of minus NTU. But to get that NTU, we require the overall heat transfer coefficient, what is the diameter of the tubes, etc., etc. But nothing was given. So I cannot use that. Actually, there is one important formula available to us. 1 minus e to the power of minus NTU over A is the area of heat transfer, that is pi dl into number of tubes. Area of heat transfer is pi dl into number of tubes. Number of tubes is luckily given, but no diameter, no length. So I cannot use this formula. That formula valid for parallel flow and counter flow if one fluid is undergoing phase change. That is when the capacity rate ratio is 0, like in this case. When the capacity rate ratio is 0, that formula is valid for both parallel flow, counter flow. So, but data is not there, I cannot use it. Then I have to go for the definition. What is the effectiveness of the heat exchanger? Q actual divided by Q maximum possible. How to get the actual heat transfer rate? Okay, actual heat transfer rate, he has given the mass flow rate of the steam. Mass flow rate of the steam is given, just steam is condensing only. See that, just condensing, it is not undergoing any subcooling. So that is why latent heat of condensation, latent heat or HFG, which is also called as HFG of steam. Mass flow rate of the steam is given, how much mass flow rate? 430 kg per second into latent heat of condensation, 2.326 into 10 cube. So you will get the answer in kilowatts, huge value, very big value. Any condenser and the retransfer rates are very, very high in megawatts and all you get. This is the actual heat transfer rate, mass flow rate of the steam into latent heat of condensation of the steam. Okay, and that should be equal to the actual enthalpy change of the cooling water. But we require the maximum possible heat transfer rate. How would you calculate? Maximum possible m dot Cp small into Thi minus Tci. Both the temperatures were given. Cp of the small means on what side? Water side. Steam side the capacity rate is infinity. Mind that here m dot H Cph is infinity, tends to infinity, because steam is condensing. Steam is condensing, it is changing its phase. It is changing its phase. It is like this. Steam is just condensing, no subcooling there. Just steam is condensing. On temperature entropy diagram, dry saturated steam is entering and saturated liquid is leaving. Actually all these wordings should have been given, but because it is a memory based, students cannot remember those words. Maybe there may be actually in the original gate paper it should have been given that a dry saturated steam is condensing into the saturated liquid. Sometimes it may undergo subcooling, then we have to add that degree of subcooling and the mass flow rate, etc. But data as mentioned by the students, because memory based, the saturation temperature was only given and the latent heat of condensation was given. It is condensing at 50 and this latent heat was given. Fine. So that is water side cooling m dot Cp. What I want to say is capacity rate on the steam side, that is on the hot side, capacity rate on the hot side, this is 50 degrees Celsius, is infinity. Capacity rate is finite on the cooling water side. So that is smaller. That is, what is the water side mass flow rate? 1 kg per second, maybe for one fluid there are 20,000 tubes are there, and Cp is 4.4 kilojoules, I guess. He has not given any specific heat. So you can take 4.186 water, 4.186 into Thi is 50, Tci is 30. This is the maximum possible heat transfer rate. Actual heat transfer rate divided by the maximum possible heat transfer rate is effectiveness. Answer is 0.71. Approximate answer is 0.71. This value depends on how well the students had given the feedback, right? See, but the problem answers I am getting, if one student give one data and another student give another data, actually because the answers will vary, but you have to understand what procedure, what steps that we are doing
to get the final answer given. But procedure will be same, answer values may be substituted maybe here this side or that side based on the data given by the students. Okay, right. This is the actual by maximum, but if the area is given, it is a shortcut method. By the area of heat transfer into number of tubes given, diameter and length, it is even easier, overall heat transfer coefficient. But data is not there, we have to depend on this. Mass flow rate per one tube is given for 20,000 tubes. Specific heat of water not given, I have assumed as 4.186, right? It's a good question. Steam always shell side, water always tube side, remember that. Yes, this is another question. This is another question which is given for a constant wall surface temperature convection. Actually options in fact maybe that students may not be giving the feedback correctly, but let us understand the question there. It is the question regarding the constant wall temperature of the pipe. So that how do you maintain this constant wall? I would like to highlight this. A constant actually in the for laminar flow, for fully developed flow through pipes, there are two different situations will arise. For fully developed flow, through pipes, both hydrodynamically and thermally, both hydrodynamically and thermally. For fully developed flow through pipes, for both hydrodynamically and thermally, hydrodynamically means your velocity profile will not change, thermally means temperature profiles also will not change in the direction of the flow. There are two situations generally we come across. One is constant heat flux. For the last 3 or 4 years, he has asked the constant heat flux. Last 3-4 times of the gate, it is the constant heat flux. That has been asked. Last year also asked. In gate 23 also is asked. 22, 21, in all the last 2 or 3 years, he was asking constant heat flux. This time he has changed to the constant wall temperature. Constant wall temperature. How that is maintained constant heat flux? How do you achieve that? Means by winding the electric power coil. You will wind the electric power coil, and by changing the number of turns from this location to location, you can call this as X direction, sometimes Z direction they call flow direction. Okay, this is a Q dot is not a function of X. This is called as the constant heat flux. Now what we are doing is constant wall temperatures. How do you achieve this? Condensing the steam. Steam condensing on the outside the tubes, we may get the constant wall temperature. Everywhere TW is same. Wall temperature is same. And another means also there, or by radiation. Or by the radiation, by maintaining the radiation. Another way of maintaining the constant wall temperatures. But what we mean to say is TW is not a function of X. Wall temperature is not a function of X. But the fluid will be, temperature keeps increasing. If you just look at the temperature profiles, wall temperature will not change. But the bulk mean temperature of the fluid keeps increasing. TB, it is called TB. Some books will give it as a TM, both similar. This is the wall temperature. This is the X direction. So this is the situation. TB is the bulk mean temperature of fluid. Some average temperature of the fluid at a given cross section. TB or TM, that keeps increasing. Okay, this is the situation. For fully developed flow, hydrodynamically fully developed means U is a function of R, right? U is a function of R at a given cross section.
but that function will not change. This function, it is not a function of x. It is not a function of x. This is called hydrodynamically fully developed. Fully developed. Hydrodynamically fully developed means this u fixed there. And if we define another function, this function, this cannot be d phi by dx is equal to 0. The dimensionless temperature variation, no? If fully developed thermally, if fully developed thermally, see, boundary layer growth will not be there if the fluid is happening there. So look at this. Once the thermally fully developed flow, if there is no further growth of the thermal boundary layer. Thermal boundary layer growth will be there only up to certain distance. This region is also called as the thermal entrance length. This is also called as the thermal entrance length. And beyond which your Hx remains constant. Actually, main thing I want to tell here is for thermally fully developed flow, where the temperature profiles do not change in the direction of the flow, x is the direction of the flow, this is x is the direction of the flow. For thermally developed flow, for fully developed thermally flow, this is the thermal entrance. So this is the developing flow. This is the developing flow. Until then, flow is developing. Beyond which, fully developed flow, your Hx will not change. From the entrance of the pipe up to that section where it is fully developed, the distance is also called as the thermal entrance length. So for fully developed flow thermally, the local convection heat transfer coefficient remains constant in the direction of the flow. I repeat, for fully developed laminar flow through pipes thermally, your H value do not change with respect to the x, if x is the direction of the flow, therefore Nusselt number remains constant. So at every location Nusselt number is a same. So that answer you may have to see. Nusselt number is a wrong, B is a wrong, this is wrong, it won't change. For example here the Nusselt number is, here the Nusselt number, here also Nusselt number is not a function of x. It won't change. Nusselt number is constant. Nu is equal to 4.36. Here Nu is 3.66. This question was asked last year, exactly last year. Same question, which Nusselt number will be more? Last year or last before year? For constant heat flux, it is 4.36. For constant wall temperature conditions, Tw is equal to constant. It is, what is Nusselt number? Hd by K. I'm saying H is not a function of x. H will decrease, from here to here H will decrease. But once the flow becomes fully developed, your H local convection heat transfer coefficient remains constant. When H is constant, diameter of the pipe is constant, K is the thermal conductivity of the fluid, that is also constant. Nusselt number is not a function of x. That is one thing I would like to tell. In both Nusselt number is a constant, but it's here it is 4.36, here it is 3.66. Of course, for fully developed laminar flow. This is not for the turbulent. Please note that this discussion is regarding the laminar only. Supposing you may ask, if it is a turbulent, yes, of course, they are also constant but different equation. And Datus-Boilter equation must be used. If the flow is turbulent, we have to use this equation, 0.023 into Re to the power of 0.8 Prandtl number to the power of n, where n is equal to 0.4 for heating of the fluid, 0.3 for cooling of the fluid. Okay, this is for turbulent flow, that is Reynolds number is greater than 4000. This earlier discussion is for the laminar flow when the Reynolds number is less than 2300. Okay.
This discussion. So, this that probable answers I can say is what dW by dx constant wall, this is correct. The wall temperature will not change, right, in the direction of the x. It is 0, that is correct. This is not correct. Bulk mean temperature changes exponentially, correct. This is very much right. Bulk mean temperature changes exponentially, it rises. Because the local heat flux, I am telling that local heat flux is more here because delta T is more. Here the local heat flux is lesser. Local heat flux is lesser. But the bulk mean temperature changes exponentially. Bulk mean temperature changes exponentially. TB changes, increases more correctly. TB changes or increases exponentially. Correct, that is. Wall temperature will not change. And when do you say that it is a thermally fully developed flow? I have already given this. This particularly d by dx of Tw minus T divided by Tw minus Tb should be equal to 0 for thermally fully developed. This is a condition for thermally fully developed. Temperature profiles must not change. This is the one you have to understand, because the local heat flux keeps decreasing. Bulk mean temperature, I could write that equation also here. Why that local heat flux is, you can see. If dq is the local heat flux, local heat transfer rate, Hx into 1 into wall temperature minus bulk mean temperature at that cross section Tb. Okay. So Hx is not a function of x, but this will decreasing. This here it is more, here it is less, it keeps on decreasing. dq becomes a function of x. The local heat transfer rate keeps decreasing. Here it is dq is more, here dq is lesser. That is why bulk mean temperature increases exponentially. Answer is, so there are so many things that will change with x, some parameters remain constant. This is constant with respect to x. Wall temperature remains constant with respect to x. Nusselt number remains constant with respect to. So what are the parameters that remain constant I am discussing? Local convection heat transfer will not change. Local convection heat transfer coefficient graph is like this. Local convection heat transfer coefficient graph is, and during thermal entrance length it keeps decreasing. But once that becomes fully developed flow thermally, your Hx is constant. Therefore, Nu is also not a function of x, because Nu is Hd by k. Only during this developing flow Hx keeps decreasing. Only from that, during that entrance length. Okay, try to understand this. The questions on this particular topic, laminar internal flows, constant heat flux and constant wall temperature, they were being asked very often in the last 4 or 5 years of GATE. But last time he is asked about constant heat flux, now this time he is asked constant wall temperature. Bulk mean temperature increases exponentially. Wall temperature is not a function of x. Hx is not a function of x. Nusselt number is not a function of x. X is the direction of the flow. Okay. And this particular temperature profile, non-dimensional temperature profiles also is not a function of x. But then what will change with x? Bulk mean temperature changes. Local heat flux decreases. Local heat flux changes with x. Wall temperature is not constant. Bulk mean temperature will increase with x. Local heat flux decreases with x. So these are the things that will change with x. X is the direction of the flow. Please remember. Local heat flux decreases.
bulk mean temperature increases exponentially. Okay. Wall temperature do not change with x. This is the flow direction. X is the flow direction. Nusselt number value is 3.66 for constant wall temperature. Nusselt number is 4.36 for the constant heat flux. Both are laminar. If it is a turbulent, you have a different equation. This is the equation for the turbulent flow. Very famous equation this is also. This is the graph you have to remember. Unlike, you see, the main difference between the flow over flat plates, external flows, this is the main striking difference. For external flows and for internal flows, what makes the main difference is the variation of this H. In case of the external flows, flow over the cylinders, flow over flat plates, flow over the spheres, the local convection heat transfer coefficient is different at different locations. Whereas for internal flows, internal flow forced convection heat transfer, once the flow becomes fully developed thermally, I had given you the condition when it will become, when is the meaning of that fully developed flow thermally. Once the flow becomes fully developed thermally, the local convection heat transfer coefficient do remain constant in the direction of the flow, both in laminar and also in the turbulent. Please keep that point in mind. This variation of H you see only in the external flows, not in the internal flows. That is why we don't have any local Nusselt number, local Reynolds number, local Staunton number. This kind of a business will not be there for the internal flows. For the external flows we have, definitely. H value, local convection coefficient will change with X for flow over flat plates, etc. Okay, these were the questions given in heat transfer. Now this is the another important subject, fluid mechanics. Actually, fluid mechanics I expected more this time because this is being said by ISC. Actually I think 4 questions were asked, but I could not get the other 2 questions. I got only 2 questions based on the memory based. One question as I expected in that, please note that in that 12 days ago I had given the video. I said, in that video very clearly I said, you will definitely get a one question from the kinematics, velocity potential or velocity velocity distribution along x direction, y direction. That this is a question on that. See that video, you may understand. Just 12 days ago I had given you the tips. So this is a question asked in the kinematics. One more question is we got in the dimensional analysis, and another question is there, flow through pipes. Definitely most commonly question asked in fluid mechanics is flow through pipes. I think discharge calculation something, but I could not get the data on that. I will discuss this fluid mechanics question. It is a mathematical question. A velocity field of a 2-dimensional incompressible flow is given by, generally this is u I bar plus v j bar, 2-dimensional, 2D steady incompressible flow. Last year GATE also has given, but there it was unsteady flow. Last year GATE 23 also has asked, but it was incompressible flow but unsteady flow. Now it is 2-dimensional steady incompressible flow. This was given. Therefore u will become 2 sine hyperbolic x and v is, of course, is a function of xy. I bar j bar denote the unit vectors. What is the Vx0 at V0 minus 1? At V0 minus 1 given this particular boundary condition. So it is the only thing is it is a 2-dimensional steady incompressible flow. The continuity equation in differential form, you know that continuity equation, conservation of mass or continuity equation in differential form for the 2-dimensional incompressible flows is given by, actually if it is a 3-dimensional flow, del V I would write for 3-dimensional steady incompressible, but this is 2-dimensional, it is dou u by dou x plus dou v by dou y is equal to 0. Dou by dou x of u is what? 2 sine hyperbolic x plus dou by dou v by dou y is equal to 0. What is this one? 2 cos hx, okay, plus dou v by dou y is equal to 0 implies dou v by dou y is equal to minus 2 cos hx. Dou v is equal to minus 2 cos hx into dou y. Integrate. Integrating, I am integrating here. V is equal to, we are integrating with respect to y, minus 2 cos, x should be treated as constant, into y, plus because you are integrating with respect to y, you will get the f of x as the constant of integration. So that f of x you have to calculate from that given boundary condition. At x is equal to x and y is equal to 0, v is equal to cos hx. I substitute that. At x is equal to x and y is equal to 0, this will vanish. Therefore, f of x, what is that f of x will become? Cos hx. Now we got the function. So final function for the v will be, final answer I am writing. What is the final answer? Minus 2 cos hx minus into y plus cos hx. So you take the cos hx common, 1 minus 2y. Put x is equal to 0 and y is equal to minus 1. It becomes, answer will be 3. Put x is equal to 0 and y is equal to minus 1. Therefore, answer will be plus 3. This is answer. Just substitute. V will be 3. Put these two conditions. He has asked, no, x is equal to 0, y is equal to minus 1. This is the final function of v. At any x, at any y, you can calculate v. If it is a 3-dimensional flow, I would have obtained this del v is equal to, for steady 3-dimensional incompressible flow, this is the format of the continuity equation. Find the value of A where L is equal to, he has given one capillary effect, one horizontal flow. So capillary length, it is a problem on dimensional analysis. It is a problem on dimensional analysis. A length of the tube in a capillary length, capillary effect, capillary length is given by K into R. This is not R, we can take this as the gamma, we can take, which is called as the surface tension. He has given what are the terms. This R is a radius, this may be the R, and mu is the dynamic viscosity, dV in Pascal second, and T is the time in second. We have to just calculate what is the exponent A. So by using the Rayleigh theorem, just equate the dimensions on both sides. L is in meters, okay, L is in meters, right? L is L, left hand side. K is only a constant, no number. M0, L0, T0, that is a constant there. Then what is the surface tension? Surface tension is Newton per meter. ml t power minus 2 divided by length. It becomes m t power minus 2. That is the gamma is the surface tension. It is not R, it is gamma. So it becomes m t power minus 2 to the power of A. R is length B. M L minus 1 T minus 1. That is the dynamic viscosity in Pascal second. That is C. So T to the power of root, no? T to the power of 1 by 2. T is the time. So equating for length L, I just equate the powers. For length L, 1 is equal to B minus C, that's it. For length, for mass M, that is 0 is equal to A plus C. For time t, 0 is equal to left hand side. T equations, no, the L is equal to left hand side t, right side it is minus 2A minus 1 minus 0.5, sorry, plus 0.5. Minus 2A minus C plus 0.5. Now you can get the value. Substitute, get that 0.5, you will get the answer. This is answer. Answer is 0.5. Actually, the other two questions were asked regarding the one is, I think, incompressible flow through pipes regarding the discharge. If it is incompressible flow, either they may ask about the laminar or turbulent. If it is a laminar flow, definitely you would be asking about the Huygens-Poiseuille equation. If it is a turbulent flow, he is asking about Darcy-Weisbach. So definitely one of them will be the condition from which you need to calculate the discharge, maybe from the head loss or so. Most probably they might have asked about the laminar flow, where we have to use the Huygens-Poiseuille equation. HF is equal to 32 mu VL by WD square, where V is equal to discharge by cross sectional area pi by 4D square. So the questions will be framed around that particular Huygens-Poiseuille equation, velocity distribution, discharge, like that. Okay. Now, so two questions of FM I have done. One is regarding the dimensional analysis, and previous one is the kinematics. This is a problem on kinematics. Generally in FM, we don't miss the question regarding the Bernoulli, but this time I don't know. This actually FM weightage also given lesser, but usually they ask about 6 to 7 marks. But I don't know, that other two questions we did not get it. So after getting the complete paper, you will come to see later. Okay. Now going to the another very important subject called strength of materials. He has asked the 4 questions regarding the strength of materials, and usually as compared to the previous year's weightage was decreased this year as compared to 23, 24, 20 as compared to 22, 23, this year lesser questions marks were asked in the SOM, strength of materials or solid mechanics or mechanics of materials, where questions depth also a bit easier as compared to the earlier papers. The first question was given like this: is UVL. UVL, a standard case of the simply supported beam UVL, uniformly varying load. We have to calculate the location where the bending moment is maximum. Okay. It is a simply supported beam. We need to calculate the location in the beam where the bending moment becomes maximum. We know that bending moment becomes maximum wherever the shear force changes its sign, or shear force becomes 0, right? That because we know that dm by dx is equal to shear force. Only when the shear force is 0, bending moment becomes maximum. Bending moment is maximum at the location where the shear force is 0, where the shear force is 0. So we have to write the equation for the shear force. First we have to calculate the reactions. Number 1, first we have to calculate the end reactions. Then draw the shear force diagram, write the shear force equation and equate that to the 0 and get the location where the shear force becomes 0, and at that location calculate the bending moment, that becomes the maximum bending moment. That is the procedure actually. First you have to get the end reactions, number 1.
then calculate, write the equation for the shear force, and equate that equation in terms of x, and equate that equation to 0 to get that location where the shear force becomes 0, and at that location calculate the bending moment. That will be the maximum bending moment. Okay. So first let us calculate that end reactions there. We just take this as A and B. So if we just take the RB is equal to like sigma MB, net algebraic sum of all the forces about the B is 0, that becomes RA into 1.2, it should be equal to the, and where is this one asking how much is the total load there? Half into base into height. Base will be 1.2, height will be 100, that is the area of this UVL load. Where is it acting? 2/3 from this and 1/3 from this. That is 1/3 of the 1.2, right? So this is the location. This is the total load, half base into height. That is the total load. Where it is acting? It is acting at a distance of 1/3. Like this is 1/3 of this distance. That is 1/3 of 1.2. That will give the this is an anti-clockwise, this is anti-clockwise, this is a clockwise. Okay, from which we will be getting the RA as 20 kilonewtons. Now sigma Fy is equal to 0. Sigma Fy is equal to 0 for equilibrium. Therefore, RB will be total load. What is the total load? Half into base into height. 1.2 into 100, that is the total load, area total load, acting vertically downwards, and minus 20. This will be 40 kilonewtons. We got both the reactions. First I have taken the moments about B, and then net algebraic sum of all the y direction forces is equal to 0, from which we got the two end reactions, RA and RB. That is the first step, right? We got both the two vertical end reactions at this hinge and as well as the roller support, and then take the, now we need to write the shear force equation. So for which I have taken one section X. I have taken one section X at a distance of A. So I can write the shear force. Shear force at X is equal to shear force at XX. We just take the XX at a distance of X from the free end. Shear force at XX, if you write, is equal to minus plus 20, left side upward is positive, minus half into X into 100x divided by 1.2. This equal to 0. Okay, this is the shear force equation. Half into X. Half into X into 100. Supposing for a distance of X, what is the rate of loading? 100x by 1.2. Half into X into this rate of loading at this location will become 100x by 1.2. So that is the shear force. Shear force at this section is, this is RA, upwards is positive. This downwards, what is the total load? What is the rate of loading at a distance of X from the free from the end A? That is 100x by 1.2. That means for a distance of 1.2, if this is the load is 100, for a distance of X, what is the rate of loading? 100x by 1.2. So we have calculated the total shear force. Left side downward forces is negative.
So left side upward forces is positive. So this is the shear force equation. Equate to that to 0, we get x as 0.693. This is a location from left side, location from A where shear force is 0. We got that location. Now at that location calculate the bending moment. Therefore, bending moment at x is equal to 0.693 from A. I am calculating the bending moment, that will be equal to 20 into 0.693 minus half into here at a distance, say for example it is 0.693, half into 0.693 into 100x, that is 0.693 divided by 2. This is a total load into, at what distance from that, it is 0.693 by 3. This will become 9.23 Newton meter. So this is the answer. Answer is, procedure is very simple actually. First you have to get the reactions, then write the equation for the shear force, equate it to 0. You will get the location where the shear force is 0 from A. At that location calculate bending moment. How do you calculate bending moment? Supposing if it is a, if it is this is the location where the shear force is 0, say for example. So at that location, from in bending moment at that location will be, you know, the reaction. Reaction is 20 into 0.693 minus what is the load acting, at what distance that load will be effectively acting if it is a UVL. Because from this distance you are taking that, from this distance we are, because we have to convert this particular triangle, we have to reduce it to a point load, that keep that point load exactly at the center of gravity, center or centroid of that triangle. When you are calculating the bending moment, we have to, particularly during the UVLs, get the total load by taking the area of the diagram and put that as a point load acting through the centroid. Where is the centroid from this tip? It is at a distance of 0.693 into 3. That 0.693 is the distance from A. Okay, that is the location where the bending moment is, maximum as such. This is answer. And if you just draw the, actually if you just look at this equation, bending moment is varying parabolically, shear force is varying parabolically, x into x square. Then bending moment will be varying cubically. So what is the diagram for the shear SFD and BMD for that? Supposing if this is the UVL, if this is a uniformly varying load, this is the equation for the, this is parabolic. Definitely it is a parabolic, because shear force will become a, now this is the cubic. Bending moment is maximum. Bending moment is maximum at that location. This is BM. This is the location where shear force is 0. This is SFD. This is BMD. This is the rate of loading. Okay, this is parabolic. I already written that. This is cubic. This is the cubic equation. Cubic equation in terms of x. So this is the problem, and look at the next question there. So this question was a solid massless cylindrical member of 50 mm diameter is rigidly attached at one end and is subjected to an axial force and a torque. This is an axial force and a torque, and the other end at the other end as shown. Okay, axial force and a torque. Assume that the axis of the cylinder is normal to the support. Considering the distortion energy theory. Distortion energy theory. What is the theory? It is a problem on the theories of failure. It is a problem on the theories of failure. Distortion energy theory of failure. It is a problem on the theories of failure. this states that the distortion energy theory states that
the member is liable to, the elastic member is liable to yield, or it may fail when the distortion and strain energy stored in the member per unit volume would become greater than the distortion energy stored in the unit volume per unit volume under the uniaxial tensile test. Under the uniaxial tension test, there is one yield point at that particular location while it is yielding. Under the uniaxial tensile test, there is one yield point at that location. There will be a distortion strain energy per unit volume that should be more than the distortion strain energy suffered by this member under the biaxial. There is a biaxial loading here. So that is the condition for the distortion energy theory. Okay. First, actually, I would like to write what is this stress, axial stress. This is a biaxial stress is there. One is axial. This is axial and this is torsional shear stress. This is shear stress due to the twisting moment. There is a longitudinal stress which is given by load by area. This is 10 megapascal axial stress. Shear stress, maximum shear stress, which is on the surface of the shaft here at this, because where you see the maximum, forget about this, because of the twisting moment, at what location you see the maximum shear stress on the surface, on the surface of the shaft. Shear stress tau xy will be 16 T by pi d cube from the torsion equation. T by Ip is equal to Fs by R. T by Ip is equal to Fs by R, that is where Ip is the polar moment of inertia, T is the torsion, and Fs is the shear stress and R is the radius, that is d by 2, that is 24.45 megapascal. Okay. Now sigma y will be 0, but supposing if we just look at the state of the stress, we have only sigma x, that is axial stress, and we have the tau xy. Sigma y is 0. Sigma y is 0. So for this condition, we have to calculate the principal stresses. Actually, the thing is we have to calculate the principal stresses, sigma 1 and sigma 2. From that, we have to calculate in fact, the question is, what is the factor of safety? He has given that with allowable yield stress is given 300 megapascal. So from that, we have to calculate the principal stress, P1 and P2, and based on that, we have to calculate the factor of safety. That is one route. There is a shortcut method from the direct formula. If you write maximum permissible tensile stress should be greater than sigma x square plus 3 into tau square. This maximum permissible tensile stress is yield under tension, yield under tensile stress divided by factor of safety, that is yield stress under the simple tension test is given as 300, should be greater than or equal to 10 square plus 3 into 24.45 square. You will get factor of safety as 4.5. This is the problem on the distortion energy theory, von Mises. Some will call it as the von Mises theory also. Distortion energy theory says that the distortion strain energy per unit volume under the biaxial stress
should be lesser than the distortion strain energy per unit volume what you see under the uniaxial tensile test. So, when you are doing a member is undergoing a tensile stress, there is one yield stress you get, right. Okay. And this particular distortion energy per unit volume should be less than that, otherwise the member is liable to fail or yield. Actually, from this we have to calculate the principal stresses sigma 1 and sigma 2. Sigma 1 and sigma 2, we have to calculate the principal stresses, and from that we have to calculate again from that we have to calculate the maximum tensile permissible stress which results to this formula only. Okay. F value is 4.5. This problem is based upon the distortion energy theory of failure or von Mises theory of failure regarding the distortion strain energy. This is the sigma y is 0, we have only sigma x, that is sigma x. It has got the shear stress because of the torsion on the surface of the shaft which happens on the surface of the shaft. This is the state of stress for the element, and no sigma y, we have to get the sigma 1, sigma 2 principal stresses for this condition, and then that should be based on that we have to calculate this maximum permissible tensile stress. Tau is the shear stress, sigma is the this is axial stress. So, in this case the statically indeterminate, what is the statically indeterminate beam? The whatever the equations of equilibrium, generally what we use it for the rigid body analysis, static equilibrium. For the static equilibrium of a rigid body, in the analysis of the static equilibrium of a rigid body, we have a definite number of equations. Sigma fx is equal to 0, sigma fy is equal to 0, sigma m is equal to 0. That means there are certain number of unknowns that can be solved with those three equations of equilibrium. But if the number of unknowns exceeds those equations of equilibrium which can be analyzed for a rigid body static equilibrium, then that problem becomes indeterminate. So, in this case there are two answers are there, indeterminate answers, both A and B. It is a multiple selective questions, both A and B. Statically indeterminate means number of unknowns to be found are greater than the basic equations of static equilibrium, available in the rigid body analysis. Available in the rigid body analysis, rigid body equilibrium analysis. Okay, that both A and B are the answers. We can't, number of unknowns are more, we can't get them, we can't solve them in fact. This figure is a cylindrical pressure vessel constructed by welding plates together along a line that makes an alpha is equal to 60 degrees with the horizontal. This is the horizontal, with the horizontal it is making 60. So, when the subjected to the internal pressure of 200 kilopascal, the magnitude of the normal stress acting on the vessel is, this pressure vessel, a thin cylinder, we can call it as a thin pressure vessel is a thin cylinder. Whenever any thin cylinder is subjected to a fluid pressure, which is when it is carrying a fluid inside, it is subjected to the two perpendicular stresses which are called as a biaxial stresses. One is longitudinal stresses acting along this direction, and other is the circumferential stress, or also known as the hoop stress. That is, okay. Incidentally, the ratio between them is 1:2. One is longitudinal stress, and other is the hoop stress, also known as the circumferential stress. So, in this case, that the state of the element will be This is the state of stress you get. This is sigma x, that it is a longitudinal, and this is the sigma y. This is 10 MPa, this is 20 megapascal. Look at this, that the ratio between the longitudinal and the hoop stress, one is sigma L, longitudinal stress, PD by 40, sigma hoop or sigma circumferential, sigma hoop stress or circumferential stress will be PD by 2T. One is the double the other actually. We can see that. Okay. No shear stress. Tau is 0 here. No shear there. Tau is 0. No shear. So we have to calculate at an angle of, see, we have to calculate magnitude of the normal stress acting on the vessel when they subjected to the magnitude of the normal stress here. This is asking the magnitude of the normal stress at what? This one. So when that is 60, so like this will also be 60, right? This is will be 60 degrees with respect to the vertical there. Okay. This is sigma x. How much is this? This is 10 MPa. No shear. This is 20 MPa. We have to just use the equation for getting the normal stress. Normal stress on the member, sigma L will be a standard formula, no? That is P sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. Cos 2 theta, then it will be 12.5 megapascal. This answer. This is a normal stress, we got it. Okay. This is the concept what we have to understand in the principal stresses also. Whenever I had given the video about 12 days ago, very clearly I mentioned the principal stresses formulas are very important, more circle. They were repeatedly asked and they will ask it again and again because they are the concepts which will be applying in the theories of failure also. What is the principal plane? Principal plane is the plane on which there are no shear stresses. Actually, how do you get the principal plane? On this plane there may be a shear stress. So if you equate the shear stress is equal to 0, you will get at what angle that plane will exist. The only stresses, normal stresses that are existing over the principal planes are called as the principal stresses. First, in the concept of the principal stresses, in derivation of the principal stresses rather, you should be able to calculate the normal stress and the shear stress on any plane which is given at a given angle. In this case, it is making an angle of 60 degrees with the horizontal, like sorry, this will become 30. I had made a mistake there. This will be 30, I guess. 60 degrees with the horizontal means 30 degrees with the vertical. (30 degrees with the vertical). Please correct it. By mistake I have written as a 60 degrees with the horizontal. Therefore, 30 degrees with the vertical. This is the plane on which we are required to calculate the normal stress. Normal stress on the plane. Yeah, so they are the questions that were asked in this. In fact, SM they have asked only 4 questions, but actually it is a lesser than the expected weightage strength of materials.
Now there are 3 questions asked in the next subject will be engineering mechanics. Engineering mechanics. He has asked what is the magnitude of the horizontal reaction. Just by looking at the overall figure, there is a hinge there, all are hinged there. There are only vertical loads, right? Here vertical loads are there acting. So, from the given figure, if you just overall looking that, whatever the horizontal reactions are there here, because hinge may have both horizontal and vertical, but for the overall equilibrium, this is RH at A should have to cancel the RH at C, because we have only 2 equations, sigma Fx is equal to 0. For that, RH at A should be equal to the RH at C, number 1. That is Ry at A, because at a hinge there may be 2 reactions, one is horizontal and other is vertical. This is Ry at C, sigma, from this what can you say, sigma Fx is equal to 0, RH at A should be equal to the RH at C. Sigma, if you write the overall equations of equilibrium, Ry is equal to 0. Before writing the Ry is equal to 0, I write the another third equation of motion, that is taking the moments about the sigma Ma is equal to 0. Sigma Ma is equal to 0. That is then in such case this is RC will be RC, Ry at C. Ry at C into 12 is equal to P into total 12 minus 6 plus 3, 9. That is P into, what is it, P load given? P load given as 100. This is 100 kilonewton, this is 50 kilonewton as given. By taking that 100 into 3 plus 50 into 6 plus 3, 9, from which you will get the Ry at C, that is 62.5. Sigma Fy is equal to 0. From that you write that, from that 100 plus 50 downwards should be equal to the Ry at A plus Ry at C. Sigma Fy is equal to 0. You will get the Ra as 87.5. Okay. So we got Ry here, Ry there. These two are equal, but we don't know how much is that, but they are only equal there. Now you can take the, for getting the horizontal reaction here, only take this part, only take for the equilibrium of this part. When you take the equilibrium of this part, there is RH at B, this will be the RH at A, and this is the Ry at A. Okay, and there is a load here. There is 100 newtons. Okay. This Ry at A is 87.5. Okay. Sigma Ma is equal to 0 if you take only for this part. If you take sigma Ma is equal to 0, moments about this point. So this is 1, this is clockwise, this is anti-clockwise, right? So you will get the, taking the moments about this, RH at B 37.5. This is 100, this is 87.5,
this will be, this is a sigma Fy is equal to 0 if you write Ry at B will be 87, Ry at B will be 12.5. Ry, this is Ry at B. This is B location only for this part. First take the whole thing, get the two reactions here, and then only take the equilibrium of this. This is 100 is downwards, 87.5 is upwards, therefore Ry should be equal to the 12.5 upwards, right? Then take the moments about A, all these, both these hinge reactions moments become 0. This is where is one moment, there is a clockwise moment, and there is another moment here like RH into this height, 6 meters, right? This is 6 meters given, from which you will calculate the RH. There is one moment here, there is one moment here, and there is another moment here. RH one moment, Ry another moment, 100 is another moment. Totally 3 are there about A for the equilibrium of this. For the equilibrium of this there are 3. RH will have a moment, Ry will have a moment. Ry, how did you get the Ry? By writing the sigma Fy is equal to 0. There is a downward force, there is a upward force. So Ry should be equal to the 12.5. That will have a moment about A. RH will have a moment about A. 100 will have a moment about A. From that you will get the RH. It's a very good question. This is, I have written for the whole thing, you write the equilibrium equation. And then you write the equilibrium equation only for this part. Okay, only for. At B, there will be, at any hinge, there will be horizontal and vertical reactions. If you take the whole thing, because the whole arch is under, semicircular arch is under static equilibrium, the reaction here and the reaction here must cancel each other. There are reactions, but they must be cancelling each other. They should be equal. The rigid massless tetrahedron, vertex as at D, has vertex D is at origin, and the other 3 vertices A, B, C. Not D, this is O. For the body to be equilibrium, the third point load acting on the point should be, answer is D, along the Z axis, this way. For the body to be equilibrium, the third point load acting at, there are 3 concurrent phases, there are forces there. There are 3 concurrent forces. 3 point loads, one is acting at A, one is acting at along the x-axis, other point at y-axis. For the body to be in equilibrium, the third point load acting at point O must be actually it seems if there is a one force here, there is another force, that resultant will fall in the xy plane, right? The resultant will fall. This question there is some ambiguity. Supposing there is one force here, there is another force. The resultant also will be lying in that xy plane. So to keep that in equilibrium, that resultant should also be in the xy plane, but should not be along the x and y axis. Answer seems to be B, because when there are 2 forces acting in a plane, the resultant also will be in the same plane, but along this direction. So therefore that becomes the coplanar concurrent forces. Then to keep there is a third force to can balance that resultant also should be in that x. It seems the answer seems to be in B, not in D.
but that should not be along the x and y axis. There is some ambiguity in this question based on the memory based data, but anyhow with my concerns I will go with the answer B. So this is also a question which was in fact this was the repetition of the question which is given in the ISRO. In the ISRO exam, which I have given the solutions a month ago, I had given the solutions for the ISRO mechanical paper. Similar question was given in the ISRO. There also same principle, conservation of energy. Here also that means sum of potential and kinetic potential energy and the kinetic energy, sum should be equal to 0 if there is no dissipation of energy, right. If there is no dissipation of energy, the sum of potential and kinetic energies must be 0. So there is a string. There is a string carrying, there are two strings carrying this RAM, okay, and geometric center is, assume the center of mass of the body as it is geometric center. For striking the object P with horizontal velocity, what is the angle theta from which the RAM should be released? From what angle the RAM should be released in such a way that it can strike the object with a velocity of 5 meters per second. Okay. Actually, assume the center of mass of the body is at its geometric center. Actually, the sum of, from the law of conservation of energy, that rule should be applied here. Same question was asked in the ISRO paper also, which was conducted a month ago. Sum of PE plus KE must be constant, right? Sum of PE plus KE must be constant. Here there is no KE. So what is the potential energy here? That is a center of mass. If you just take this, when it reaches this, right, when it is striking here, the same RAM is striking here. So this is the one distance initial, and when it reaches this one, this height difference we have to take. When it is reaching here, the total distance will be 7 meters. But when it is here, this is the height difference, right? So what is this height? First of all, we have to calculate this height first. That is MGH here, MGH should be equal to the half mv square. M gets cancelled here. That height h, if you just take this, height h will be (9.81) into 7 into 1 minus cos theta, difference of heights. So this height will be definitely not 7, it will be less than 7. When it comes here, the total distance will become 7 there, should be equal to the half into v square. Velocity is given, this theta will be 31.48 degree, 45.1 degrees. It is simple if you can take like a pendulum, like, right? When the pendulum is handing here, so this height difference, if you just take a pendulum, simple pendulum, right? So this what angle is this? But it is not pendulum here, it is a RAM. Just like a pendulum is left, what is the difference in heights? Initially it is here, when it is reaching here, here. So the difference in height will be, the change in potential energy is this corresponding to this height, corresponding to a pendulum released. Okay, but here it is pendulum, here it is RAM. Similar thing also was asked in ISRO. You can check that paper also. So this is the theory of machines question, that here the answer is 30 radians per second. Here the answer is 0. 15.58. Here it is the coefficient of viscous damping. .41. Here it is the change in that energy was given, the change in kinetic energy is given. It should be I into omega mean square into Cs, from which I is obtained as moment of inertia 0.096. Coefficient of fluctuation was given 0.05. Omega mean you have to take 220 and 280 mean, and change in kinetic energy was given, this is 300. Omega mean will be 200 plus 280 divided by 2. Take care of the units. Which one of the following failure theories is the most conservative design approach? It is a Soderberg line. Answer is A. The theories of failure in the design is a more conservative design approach for the fatigue failure. Here the answer is D. Ball bearing fatigue life in millions of revolutions was given, where P is the constant applied load and C is the basic dynamic load rating. Which one of the following statements is true? The answer is D. And this is a brake problems were being asked very often. Brake in the recent, for the last 4 or 5 years, brake problems continuously asking. It's a band brake. Okay. The wheel is rotating like this. Therefore, it should be the tight side. It should be the slack side, right? This is T1. This is T2. Tight side, this is slack side. Tension on tight side, because direction of the rotation is given. Tension on tight side, this is the tension on slack side. T1 by T2 is equal to e to the power of mu theta. Okay, that is one. And I think that theta angle was given there. That is one equation you get. And another thing is sigma moments about A. Sigma m is equal to 0. Sigma ma is equal to 0. From that, you will get the maximum bearing force. Only two equations. One is the ratio of the tensions based on the friction, coefficient of friction. Okay. And the other thing is the bending force. This is a question given in the design regarding the band brake. Mu is the coefficient of friction given. I think the angle of friction is also given. That is lapping angle of theta is also might have been given. And by taking the moments about A, you will get the force F. This is given the 29th question is C. kelvins. Here, in fact, solidification time is a relative. Solidification time is repeatedly asked. Answer is 1 here. Answer is 1. That very most repeatedly asked question in the casting is solidification time. This is given as heat supplied. This one also I mentioned in the last time video that is always the voltage or characteristics. We have to give the percentage loss of heat. We have to give the more attention for the voltage or characteristics. This is what he has asked. Percentage loss of heat to the ambient from the law of conservation of energy will be heat supplied minus heat required for the melting, heat of melting should be given to the ambient. How much heat you are supplying, how much heat is utilized for the melting of the weld, and the balance must be rejected. That should be equal to the 66.67%. Energy supplied minus energy utilized. That gives the loss of heat. This is the D, low alloy steels. There is only one question asked in the material science, only one question material science actually, that is B is the answer. In fact, in the metal cutting, he has missed the orthogonal. Actually, generally in every manufacturing gate question, one question definitely will be asked about the orthogonal turning or the merchant circle or the shear angle, rake angle or the shear plane or the mechanics of the metal cutting. But they have missed here. But every gate one question will definitely come for 2 marks. But somehow in this particular thing, this is directly Taylor's two-life equation, even simpler question. Taylor's two-life equation. Very simple question. This is much simpler as compared to the merchant circle mechanics questions, etc. V t to the power of n is equal to constant. You need to just get the exponent n. He has given the V1 T1. V1 T1 to the power of n is equal to V2 T to the power of n. You have to just get the n value, n is 0.285 and use it again for the V1 T1 to the power of n is equal to V3 T3 to the power of n. Answer will be time T3 will be 21.87 minutes. Taylor's two-life equation question was asked in the machining operation or the metal cutting, which was very, very, very simple. In fact, this is not the expected question, rather I was expecting the orthogonal turning operation, but that was missed here. And the metal forming will be, that is answer will be blanking operation. The panel size used is 20 minus allowance, that is 19.96 mm. Where the radial clearance not given, actually radial clearance will be given usually, radial clearance not given, this is the answer. Thirty-sixth question, it is a deep drawing. In fact, forming he has asked about 4 questions. Generally, more than expected have come from the forming. In fact, I was expecting more from the metal cutting or machining operation, but he has asked more in the forming there. Deep drawing and one milling, it is the slab milling. Answer is 2.23. It is a slab milling operation. Generally, usually milling question is expected all the time. Grinding wheel. This question is regarding the one point that this number, grain size number is directly proportional to the 1 by grain size. Finer grain size means more GSM. You can see here the second number is that is second number. So where it is highest, 80. This is the answer. When the grain size is more, when the grain size is more, finer grains finer
Finer grain size means more finish, means greater finish, greater surface finish. So answer is A. This is the G answer. Industrial is asked the 5 questions, industrial engineering and operation research. Answer is W, X, Z, V, Y, U. Based on the answer is C, based on Johnson's algorithm. Based on the Johnson's algorithm, C is the answer for the industrial engineering 40th question. Here in a workstation with a single server, the job arrive at 5 jobs per hour and service rate is 6 minutes per job. What is the probability of the system that is idle? Here the lambda is given as 5, mu is 10, S is equal to lambda by mu, that is 0.5, P of O is equal to 1 minus rho, that is 0.5. (42) question is 25% percentage increase in inventory cost. Then this is an assignment problem. Answer is 12,300. Actually, there is one more question is also asked regarding the simplex method, but the data was not there. So one more question is also asked regarding the 44 question you may take. There is a simplex. There are 5 questions totally in the industrial engineering and operational research. This is an assignment problem. Answer is 12,300. And some mathematics question also I had given the, and I had got the solutions there. Here the answer is 0. 44 question. This is 70.53. This answer is 19. This is 21. This is actually. This is B answer. This is 25. Minus log 4. This is A. This is C. This is 0.39. A is 4, B is 14. (51) is 0. This is 70.53. This answer is 19. Next answer is 21. For the aptitude questions, 5 questions only. This is I got the answers. So this is the overall paper. If we just look at that, if you just look at the overall paper, neither the SOM questions are tough, nor the mechanics questions. Mechanics questions you just need to use those particularly. One question is a little bit confusing. That particular RAM question,
because where to take that center of gravity, because the weight of the ram will act through the center of gravity, right. So, up from the string length from the tip to that center of gravity location, and after finally before hitting the object, the center of gravity location, where is that? That difference in heights we have to take. If it is a pendulum like ball like that, it is very easy to make it, but there the exactly where is the string location he has not mentioned, okay. After all, that problem is regarding the conservation of energy. Sum of the potential energy plus kinetic energy should remain constant. So, but the exact vertical height in the center of gravity, the vertical drop in the center of gravity, that is important there. So, that multiplied by the mg, right, mg should be equal to the half mv square, m will get cancelled, then you will get that what angle that will be. So, that is some slight ambiguity is there in that engineering mechanics question. That was similar to the ISRO question which was asked a month ago for the scientist C post. But overall the paper seems to be moderate, it is not tough paper at all. I cannot rate it as a tough paper. It is definitely easier paper as compared to the 23 and 22. Okay. So, that topper will get slightly more marks and cutoff also may slightly increase. I hope you have understood the topics which I have dealt. Wish you all the best. This is Sekhar from M Sigma Gokulam. Wish you all the best. Good luck, boys.